Okay, welcome back. I do. Excellent. Okay, so yesterday we did this problem where it's kind of gross. I tried to annotate through it, but remember on a lot of these problems, what ultimately winds up happening is we have two unknowns, but only one equation. And then we have to solve one with a variable in it and substitute it into the other. Like that's a pretty common technique, and we'll see things like that again. Today, we're going to jump in to another type of problem and hopefully find some shortcuts along the way where we're just doing applied stuff. And our example for the start of class today is radioactivity. Anybody like super into chemistry or physics stuff? All right, so check this out. Example, we're going to make up an element here. So right now, how many elements are on the periodic table? I think it's 119 right now. I could be wrong. Oganesson or something. I don't remember. I don't know. Is it 119? Okay, so it doesn't matter right now. Turns out that cranium, and we'll say it's crazy. We'll say it's cranium 271. I don't know, some isotope of this new element that Crino discovers or creates, whatever. Cranium 271 has a half-life, and we're making up this problem. So it can be from anything. Half-lives can be minutes. Some elements have a half-life of minutes. Some of them have half-lives of thousands and thousands and thousands of years. Krina, your element, what's its half-life? 1,200 years. Okay, so before I write this, let me decide if this is what I want to do. Yeah, 1,200 years? I'm fine with that. 1,200 years. Okay, so a new deadly radioactive isotope. Sweet. I want to know, and this is going to feel like we don't really have the answer, how long until, yep, we're going to have to change this. How long until 2 grams remain? If we started with how much? Has to be more than 2 grams. That's all I care about. 25 grams? Okay. So we have 25 grams of this crazy radioactive thing. Now, for this, oftentimes when we're using these models, and I know that when we wrote them yesterday, whether it's exponential growth or decay, correct me if I'm wrong, but I think we wrote AE to the BX. Okay, I changed letters. And I didn't change them yesterday, but I changed letters depending on the context. On this one, there's not a good reason other than it's how I've always done it, and it's how a lot of textbooks do it. If you want to use this model, first off, is it growth or decay? It's decay. Now, here's the thing. When I write decay, it doesn't matter whether I note that B is positive or negative. We're going to get this out in just a moment that the B value will wind up negative. So when I write this, I'm going to write it as y equals, and we can use AE to the BX, that's valid, but more commonly in this, it's AE to the KT. This is the more common model, and specifically, this is more common because instead of X, most things in our real world work with respect to T, which what's T? Time. So it makes sense that we would use this. Where K is like our growth or decay rate right here, but it's the same model, right? AE to the BX. Okay, let's try to figure out how on earth we're going to work this out. So we're going to do another version of this problem here in just a second, but let's think it out. What does this represent again? And whether you write it or not is up to you. Final amount. What is this? The initial. And I'm not going to do T. I will, but I don't think we need to. What's T? Time. And what's K? And that's all right, because you've only heard me say this once. I'm going to say it's the decay rate, is what I would call it. Now, for this problem, and we're going to switch it up here in just a second, and we'll do a slight variation of this, but essentially it's going to follow the same sort of setup. A bunch of these problems are going to start here. What do I know? So in the end is 2. So what is that? So y is 2, because I see, and I'm just going to color code here, 2 and 2. Okay, that's my final amount. I end up with 2 grams. And that comes from how much initial? 25. So I'll underline in blue and say, check it out. There's my blue. They're both there. 25. And what else? So e to the k, and we don't know t, right? Okay. All right, rather. How many unknowns do we have here? 2. How many equations? We only have 1. Huh. Now, this one's going to feel a little bit different. Could we do the same thing that we did yesterday? Kind of. Like, if I wanted to rearrange this, I could solve for k or t, but it's going to have another variable in it, right? Now, compared with yesterday's, I've only given you 1 point, right? Is that true? Or do we have 2 points here? How many ordered pairs do I have? Like yesterday, if I go back to that example, and I think it's over here, if I look at the example from yesterday, and I'll come back to that in just a moment, we really had 2 ordered pairs, right? Do I have 2 ordered pairs on this one? Kind of. I know at times 0, it's 25, right? Can we use that? So we get 0, 25 is on our graph. And this other one's, do we know it? What is it? 25, 2. So careful, because that says after 25 years, we get 2 grams. I don't know it yet, but it's t, 2. Like, and there's an issue there. Now, there's a couple ways that we could go through this problem. And because we're going to do another variation of this in just a moment, I think that the natural way to do it right now is based on the model that we have in the numbers, can we solve for anything? Like, should we try? What do you want to try to solve for? And if it winds up wrong, it's okay. We'll just cross it out. We'll try again. It's not the end of the world. Okay, we're going to solve this for t. I'm fine with that. Thanks for committing. So all I'm going to do, because it's not me just leading us through, and this is purely off of your guys' suggestions, let's solve for t, and let's see where it takes us. And if it works, awesome. If it doesn't, awesome. Okay, so let's think it out. Do you want me to do it? How about we all do it? I'll give you a head start, though. Talk with your neighbors, rearrange this equation so that there's some dots that I'll fill in a second, but I want you to end with t equals something. I'll give you a moment. Play the algebra game. Go. We'll meet back in about 60 seconds. It doesn't really matter what we started with. If I'd started with, and don't change yours, but could I have started with 25? And how much would remain after 1,200 years? And we could have gotten the same thing. It doesn't really matter what we pick with, which is why I forced us to use the even number, because it divides by 2 nicely. So let's use this little thought, and this is just legitimately just a thought related to the problem, but obviously it feels very disconnected. Let's see if we can plug in stuff here. Well, let's just try our model again. What do we know we're using y equals ae to the kt. Like, this is still the model that we're using. And the issue was that we didn't know k, right? So maybe we can use this information that we just worked out with any random numbers. Maybe we can solve for k and get an actual number out of it. So let's try. Let's just plug in anything from this little piece that we're thinking about to see what shakes out. What's the final amount in this now new problem, seemingly? 2 is the final amount. And the initial amount was, and that's times e to the k, and how much time do we let pass? 1,200 years. Do we now have a way to solve this for k? Now, before we do this, and I lied, we'll summarize something here because there's a super handy shortcut that shakes out. I want you guys to solve this for k. You will need a calculator. I'll give you a moment. Solve this for k. And I know it feels like a different problem. It's not, just different numbers. I'm going to make a little claim, and you guys don't need to write it yet because we'll make sure we focus on it. But I think that if you look at any of your work, what you're going to find is no matter what we started, if we go 1/2 life, when I do final amount divided by the initial, it's always going to be 1/2. Like, it has to be. So you guys probably have 2/4 written on yours, but it's 1/2, right? If I'd started at 5 and I had 2.5 left, I would do 2.5 over 5, and I would get 1/2 again. It's always going to be 1/2. What's in your denominator? And what is 1,200? It's your half-life. This will happen on every single radiation problem. Every single radiation problem. Now, if you weren't able to solve for K in the first place, I'll give you a second. Everybody's writing this down now, apparently. Every radiation problem. And it's valuable and super easy to work with because no matter what, a half-life is always going to give us a 1/2 when I do final over initial. Okay, this is now an easy way for us to get the value of K without having to do this thought experiment every time. Now, this idea is important and you will use it. I happen to remember it, and when you do 2 or 3 of these now, you will remember it as well, I think. This winds up being a pretty big idea in a field of calculus that we'll look at a little bit next year. Okay, back to this though. If I want to solve, just so I can go through here, and I'll give it a second. Still see some people writing. Okay, if I want to solve this for K, I want only things with K on one side initially. How do I do that? Divide by 4. Now notice this is exactly that 1/2. This is final over initial. So I'm just going to change it to 1/2 right now. Equals, and then I would have e to the, I'll write it like a normal person. I'll write it so it's legible. E to the 1200K. How do I undo this? So I'll take the natural log of both sides. Natural log of 1/2 equals, what happens when I take the natural log here? Okay, I heard several murmurs. I don't know. What did you say? Okay, I thought you said nothing. Yep, that's just my bad. Divide by 1200, right? And now it's, I hope, obvious to you that regardless of the numbers that we pick, did we just get 1/2 and half-life? It's going to happen every time. Like, this is worth knowing. So what? So what if I know K? Oh, now I can find T, right? So using, and I'll just do this, using K equals, and I don't know what this number is. It's going to be a super ugly decimal. Negative 0.000 something. I don't know. But it says, if you've typed it in, is it still on your screen? Okay, do you have it typed in? Can I see it? Okay, so check this out, because you guys are going to, and yours did not, oh yeah, it did, okay. Just a quick verification thing on your calculator. You guys have been doing scientific notation and chemistry also, right? At least a little bit? Okay, do you guys get to use calculators? No. Cool, or not, I don't know. Okay, looking at this. When we type in natural log of 1/2 over 1200, this is the number that I get. What is the number written here? Okay, how many of you know, I think Karina does, do you guys know what this capital E means when it shows up? Times 10 to the, this is exponentiation with base 10. It's common exponent. This is times 10 to the -4, which just moves this decimal 4 to the left. 0.0005776. So 5 thousandths is my rate. Like, cool. Sorry. Okay, so looking at that, we don't need to actually have the number yet. I don't really care what it is, but we use this, we get the following. T is then equal to whatever our calculator says, natural log of 2/25 divided by K, which is a natural log. And I'm going to write this ugly, and I want your guys' help to see how do we type it in, because it's going to be awful. How do I type this in? Because this is how many years we have. Any suggestions on what I would do to type this into my calculator? So I'm going to write it exactly as you read it. Natural log of 2/25. So I'll make it look like your calculator. Okay, here's one option. This is key for key what you're going to type in your calculator with left parentheses and right parentheses added. It's not what I would type into my calculator. I would type this in. That's a 2. It's supposed to be. 2/25 over the natural log of 1/2. What did I do? One more time. Why? Did you guys catch that? We're dividing by a reciprocal, right? I'm just multiplying. Sorry, I'm dividing by a fraction. I'm just multiplying by the reciprocal. Realistically, I don't care which one you type in. I think this is less likely to make mistakes because less parentheses needed. When you type it in whichever flavor you've typed, this one or this one, hopefully we get the same approximation. And I'm going to erase the box. And let's verify that whoever feels confident with your calculator, I want you to check the ugly one. And then if you're really confident, just go ahead and check the other one. We should get the same number. Yeah. 4372. Point. Okay. So years right now, right? Because that's our unit. Okay. Anytime we're doing a problem, it's always worthwhile. And I know not everybody will do this. Like checking answers is always good. I don't really think we necessarily need to truly check it, but I do think it's worthwhile to actually think it out and see if this makes sense. And I just want to play the game real quick. This is how many years we got, which that's almost 4 half-lives. Like it's between 3 and 4, because 3 would be 3,600 years, and this would be 4,800 is 4. It's between them, right? So all I need to do is just see if we're like ballpark. We started with 25 grams, right? So check it out. We're just going to think this out. We don't even have to like calculate or anything. 25 grams. We wait 1,200 years. There's our first half-life. How much is left? 12.5. Now, we know that this many years is between 3 and 4 of them. So after one half-life, there's 12.5. Do another half-life. How much is left? 6.25. Do another half-life. So we're at 3.12, essentially. I'm just going to call it 3.1. Now, if I do another half-life, I'm at 1.7 or 1.6, but it's not quite a full half-life. Is that reasonable that I'm at 3 and I'm getting close to 2? Like I'm trying to find 2 grams left, right? Did that seemingly make sense when we just cut it in half 3 times or 3.5 times? But I don't do the half in my head. Did the number seem to match? How many of you understand what I just did when I was talking? Okay, so check it out. I'm going to write it because you will, and I assure you will. Please never hesitate to say, Holloway, I don't know what the hell you just said. Like, you can even say it like that. I really don't mind. If it's uncomfortable for you, good. But check it out. We started with how much? 25. And I'm just checking my answer right now in my head. After one half-life, which is 1,200 years, how much is left? After another half-life, so now we're at another 1,200 years, but I'm going to say 2,400 right here, right? Because that's how far we've gone. 2 half-lives. How much is left again after another half? Go another 1,200 years. Now, we decided like this together, can we all agree it's 3,600 years? Which is not quite what we needed to wait. But if I went another full half-life, and I'm now at 4,800 years, I don't know what this would be, 1.5 something? 5.6-ish? 5.625? It doesn't matter what the actual decimal is. If I wait all 4 half-lives, that's way too little. But is this kind of close to 2? Does 2 exist between these 2 half-lives? I'm convinced my answer is fine. Okay, that's all I'm doing. And I was just thinking that out because I don't think you guys need to write it to divide by 2, but maybe I need to make sense of what's going on. Okay, real quickly, last thing. We're going to play one round of the uncomfortably intense eye contact game. And here's my question. Given a radioactivity problem, how do you find K? I'm going to go get a drink of water, and then we're going to play. And just for the record, I have a bottle of water, but I'm going to step out for a very intentional purpose. How do you find the value of K in any radiation problem? That's a question that I'm going to make really intense eye contact. You guys get some time today. We just worked out the rest of the half-life stuff. What are we doing tomorrow? Bet. Practice, test. tomorrow. Okay. What I kind of like the way that I've been doing them. I don't really care if we check them for a quiz or not. That's not really whatever for me. But what I do like is having you guys, we're working away toward note cards, remember. For this, do you want to make your own one note card? This time we're going to not do any examples on them. Do you want to make the note cards before the practice test, or do you want to go through the practice test where we have before and say open note when you need, and then we can use that? I don't know if I really made it clear that there were options. I don't feel like I gave you an option. I just did a lot of talking. Okay. I want us tomorrow. There is no option. Tomorrow, when we do it, we're going to do it just like we have been, where no note cards at first. If you need to open your notes and stuff, you can do so. And then you'll think about what topics, non-example topics, but what topics are going to include on your cheat sheet. Okay. I'm debating if I want to make some spare cheat sheets that I would use with only concept, because no examples make it weirder.
There's no example when you get, like, one big step I've done before is not.
Well, on this one, I'm okay with it. But when I think of no examples, I think of like this, natural log of xy. Like this is not an example. It's ln x plus ln y. This is a definition, right? This is not an example. But if you, I'm okay with this, but I would rather not have this. Like this is very similar, right? We're going to have to use this. This is a property. This is an example. I don't want that one. Does that make sense? Okay, and it's weird for you guys, especially because you're on the road. I don't know how I'll grade it or if I'll grade it. But try not to open your books until you need it, okay?